we're down to chapter 5 here, which is heap overflows. So I'll talk about that and probably demonstrate ED 105 during lecture, just like last time I demonstrated ED 204 during the lecture, because it's pretty much just following one of these projects to see how it goes. So let me get my slides up. All right, so we're doing heap overflows. All right, so what we've been doing up till now have been stack overflows, which are the more common and more easily exploited thing. But the heap is another area of memory where you can store data, and you can also have overflows there. So the info proc map commands will show how memory is used. You can also see it in the debugger in Windows by just right-clicking and viewing memory map. So if you run info proc map, you'll see, here I'm running the program we're going to use a little bit later for demonstration. There are some Linux libraries here, and some more Linux libraries, and then there's a stack here where we've been exploiting it, and there's also a heap reserved. And so the heap has chunks of data, and the way it works is you reserve a chunk of data, and then you reserve another chunk of data and another chunk of data as you use it, and it has some control values at the top, the size of the chunks, and then pointers to the next and previous chunk in front of each block of data. That's how it works. So you use malloc to allocate a space, and when you're done with it, you use free to remove that space and therefore make it available. Remove the data, well, to indicate that the data there is no longer in use and free up that memory to be reused later. That's the idea. So here's the simple example we're going to do project ED205. You have a data structure here, which is going to be name 64. Then the next thing we're going to put on the heap is just a pointer. Then we're going to have a winner level and a no winner. We're trying to execute the winner function, just like before. And so the main function uses malloc to reserve a place to put the data and a place to put that pointer. And then we assign the pointer to no winner, print some addresses, and then execute that location. So the point is we get a chance to put in some data here. This takes int_argc ***argv means it will take command line arguments, and the command line argument is this argv1, and that is copied into the name. And the name is dname, that's here, D. This object D, the named item, and the point is the name item only has enough room for 64 bytes. And there's nothing here to prevent you from making that argument longer than 64 bytes, so we can have an overflow on the heap. That's the point here. All right. So let's just follow this project, is the best way to do this, I think. So here's ED205. Now I should have my emulated machine here running an AMD processor, because you do have to have an AMD processor for this one. And there I am, good. So if you have a Mac M1 or later, then you should run an emulated processor the way I'm doing it in this UTM program. All right, and now I'm in. Let's see, I don't want to be there. I want to be here. Okay, so, this is ED205, I think. Let me check what I'm doing. Yeah, it is ED205. Let's make a directory for ED205 and go in there. All right, and now the project is here. I don't need this on this machine. All right, so we're going to download the source code from my website, and we're also just going to download the precompiled executable, which is why you have to have an Intel compatible processor for this one. So then you do chmod +X on the executable, and now you can run it and give it like hello, and all it does is it carries data in FP, level has not been passed. So that's the game. Now, we've looked at the source code and already talked about it. The important thing is to notice that the data has a name for name 64 here for a data structure. So when we allocate that, we only have room for 64 bytes to put at the name, and then we can override it. So we can observe the heap. Let me bring this up here. So we do, let's get rid of this one. All right, so we do GDB -Q ED205. All right, and we'll list 31 to 34. So So here you are. This is where it's going to have the overflow right here. This stir copy is going to copy argv1 into the name without limiting it. So we're going to have a breakpoint at 33. Before it tries to use the data, which may be corrupted, and then we're going to run it with AAAA. Right now we do info proc mappings, and we can see the heap here. Heap is at that address, so I want to examine that address. I'll just copy it here. So it's x130x. I need quite a bit of it to see, and then that address. And so here you see it's nothing but zeros in this part. So when I press enter to see more, there it is, 41, 41, 41, 41. So that's what I wanted to show you. I put that data on the heap. And notice before it, there's some more data. And these will be something like these, say the pointers to the next and the previous block are somehow encoded there. So that's a heap structure with only a little bit of data on it. All right, so now we can disassemble no winner. All right, and get this address. And it looks like it's exactly the same as that. That's pretty cool, probably because it was pre-compiled. It's exactly the number from my examples, which is handy. All right, so now we're going to observe a crash. So let's get out of here and nano H1. And there's my attack, which is just going to put out 90 capital A's. All right. So we want to chmod and put that into a file, I imagine. Okay, just chmod. All right, and then we can run H1, and it prints out 90 A's, and we can run ED205 and feed in the data from H1, which is how you do it with a dollars parentheses. I like doing it this way, not parentheses, but dollars. This is an old-fashioned way. The modern way is to use backticks, which I think is much more confusing. So that means you run this command inside there and take the output and put it here as if it was part of this command. So that'll run it with 90 capital A's, and now I get a segmentation fault. So this is the procedure we always follow. First, you find a vulnerability if you can. If not, you just fuzz for random chunk to find it. Then you start with a denial of service condition where somehow you caused a crash. Then you try to improve that crash to see if you can control the machine instead of just crashing it. So we're going to modify the file to spend 70 and then some non-repeating stuff. So it's going to be buffer A 70 plus byte stream of, okay, 001. All right, and that's 20. So it's still the total length is kept the same at 90, which is what I always like to do to make sure I'm always hitting the same spot. And now we'll use the debugger again. And we'll run it, taking the data from H2. And there it goes, and it crashes on 35, 35, 36, 36, which is 5566. And you can see it if you do info registers. The EIP is now 5566. So I know which characters controlled it, so I can now precisely hit the EIP. And I think my example here will be correct. Well, that's 1, 2, 3, 4. I guess I can do that, but I'm going to skip that. I'm pretty confident I can hit the EIP. I'm just going to skip right ahead to the end where I put in the actual address I want. So let me get it here. Disassemble winner. All right, I want this address right here instead of 5566. So I'm going to quit. I'm going to copy H2 to H4, nano H4, and put in a comment with the address I want. And so it's going to be, instead of 5566, I'm going to put in those things backwards. So backslash XCB 840408. That's these 4 bytes backwards. And there's some horrible colors, so that's invisible. I always have to Google this. Must have Googled 100 times. Get rid of colors. There's some way to do it in Nano. Whoever put colors in Linux command lines, I wish they'd just knock it off. The config file. No. There's a way to turn it off. There. Set quiet syntax disabled. I guess that's it. Set quiet syntax. This is surprisingly difficult. There is a command in Nano to get rid of it, but everybody's giving me complicated answers. There's a simple answer somewhere. All right. Set, okay, I guess it is this set. No, that's still the wrong thing. That's the stupid thing that has to be in. Alt-Y. Just there. No. Oh, you can use -Y none. Well, that's interesting. You can set up an alias to disable, write these into NanoRC. All right. All right. I thought there was an easy way, but I can't find it. Anyway, all right. I'll just have to tell you, this is CB840408 in invisible writing. I'll get out a Nano and do a type to try to do it in the terminal, because nobody can see that garbage. Let's hit the plus, though. Let's have a quote here, and plus a quote there. So I think that'll do it. Let's cat H4. There, okay, and now they didn't make it unreadable, CB840408. And let's make sure this works. H4. Looks like it does work. 0, 2, 3, 4, 5, 6 are missing because they're unprintable. So I think we're good. So let me go back to my instructions here. And all right, so you found an address to inject. So now we're just going to run the exploit. I guess we don't need the 204. We just need to run it on H4. I guess it's 205. Set style enabled off. Thank you. Chessa figured it out. That's good. Great. Okay, now, good. Let me try that again. I thought there was an easy one, and somehow, no, there's no way to do it here in Nano. That's in the debugger, set style enabled off. There, I don't know how to do it in that debugger. I think there's a key press or something to do it in here. Anyway, there's somewhere in the options or something, there's some way to do it in Nano, but anyway. All right, so anyway, so that's what you do. That's what I wanted to show you about ED205. And let's just get back to the here and see if there's more to say about these. So there's the exploit, there's the crash, there's the targeted exploit. All right, so that's a contrived example where we overrode some data and hit a pointer that was there. We didn't find something that's always there, like a return pointer. So that's a kind of contrived example. But anyway, let's talk. Here's the problem with the heap. The heap does normally not contain pointers that go into the EIP. So you don't normally get the EIP directly from that. However, it has addresses that are used for writes. Consider what happens if I have a node storing some data and another node, and then I free this one. Then it has to take this pointer and change it to point to the next node here, and the return pointer it has to take the next node here. And if what I did was override this data, so it overrode the control data here, then I control an address that is the next pointer is used to control a write, and I control the value that's written in there, which is also coming from here. So the end result is if there's a free of something after a heap override, I can control an arbitrary write operation. Now, this is not direct control of the EIP, but all you have to do is write to some location that will be used to control the EIP. So you could write to the stack, like buffer overflows. What I usually do is write to the global offset table, which controls how you reach C libraries. If GDB uses unreadable colors, execute this command to get rid of them. Yes, that's GDB, but I was in Nano. And there is some way to get rid of them in Nano too, but it's too hard to find. Anyway, there's also destructors table that are called when the program exits. And I say the global offset table is used to reach the C library. So that's one thing you can do. And usually what you do in all the projects here, what I'm doing is just overwrite one of the C library functions. So when the program calls that library, it'll be calling my code instead. There's also something called an @exit structure that will be called when the program exits. And in Windows, the default unhandled exception handler is one place you might want to put it. So that's it for that. Let's try a Kahoot, which is chapter 5. All right. I think the people that invented Dano were trying to put in fancy features to make it appeal to people that would rather use a graphical text editor. But anyway. I'd like to just have it the way it was back in the old days when monitors only had black and white. That would be more efficient. Anyway. All right. Looks like this is it. Oh, maybe not. Okay, I'll wait a bit. Yeah, Vim is another way to go. I don't know if Vim has these stupid coloring rules. VI and Vim, that would be another way to go. That's the more professionals learn to use VI. I'm very clumsy in VI. I never got used to it. I got used to the old-fashioned syntax of things like Nano. Anyway. But you're right. Vim or VI might be a good answer. If they don't put stupid colors everywhere. All right, so what command reserves space on the stack? Ordinary local variables. You define them like this. They appear on the stack. That's where they're stored. All right. All right, so what GDB command will show the location of the heap? Yep, info proc mappings, that's it. All right, what command creates a new chunk on the heap? Malloc. You reserve some space on the heap and give it a, and T is going to be a pointer to that beginning of that block of memory on the heap. All right, which command moves EIP to an attacker-controlled value when the stack overflows? Return. That's right. When the stack overflows, you can overwrite the return pointer, and when you hit return, you gain control of the box. Good? All right, which command becomes an arbitrary write after a heap overflow? Or causes an arbitrary write would probably be a better way to phrase it. That's free. When you free the chunk, if you manage to have an overflow condition, you'll be able to write some data can control both the data that gets sent there and the location it gets written to. All right, which command allows direct control of the EIP after a heap overflow? None of them. That's the thing about the heap. The EIP is not on there. There isn't a return pointer. You have to do something indirect. That's why stack overflows are simpler. You can directly gain control of the EIP. Heap overflows let you write to areas where you shouldn't be writing, but they don't directly give you control of the EIP. All right. Good. So, let me stop this recording.